Good morning and welcome to our webinar on developing maths and English language skills for Cambridge IGCSE Science. I'm Tamsin Hart from Cambridge University Press, and I'll be hosting this webinar for our speakers, Dr. Mark Winterbottom and Sally Burbeary. Thank you for joining us today. I'm just going to give attendees a little time to join the webinar before we start. If you'd like to chat to one another and let us know which country you're joining us from, please feel free to use the chat box. It'd be great to hear from you. So thank you for joining us for our webinar on developing maths and English language skills for Cambridge IGCSE Science today. I'm Tamsin Hart from Cambridge University Press, and I'll be hosting this webinar for our speakers, Dr. Mark Winterbottom and Sally Burbeary. While we wait for more attendees to join us, let me explain how we're going to run this webinar. We're recording the webinar today to share with you afterwards, so don't worry if your internet drops out, just rejoin us when you can. If you're having trouble with your speakers, we suggest using headphones or checking that your speakers aren't muted. Your microphones will remain muted throughout the webinar. If you have any technical issues or questions about our science products, please can you put these in the chat box, and my colleagues Laura and Caris will be on hand to help you. Please can you put any questions for our speaker into the Q&A box, and our speakers Mark and Sally will answer those at the end of the webinar. 7 days after the webinar, we'll send you an email thanking you for your attendance with a link to the webinar recording and information on where to find the webinar slides. Unfortunately, we can't provide certificates. However, you can use this email as proof of your attendance. Okay, so that's the end of our introduction. Thank you very much for joining the webinar today. In the first section of the webinar, Mark will focus on math skills in science. In the second section, Sally will discuss English language skills in science. Now over to Mark.
Good morning. Thank you, Tamsin. It's a pleasure to be here as always. Well, I say as always. I'm the last time that we were doing a webinar together, I think, was just before the pandemic. And in fact, I think schools in China had already shut and schools in Europe hadn't yet shut. And I remember a huge number of questions about dealing with the pandemic. And look where we are now. We're 2 years on. And we're back in a webinar, and as always, it's an honour to be here with a wonderful group of teachers from around the world. So, who am I and what are we doing? So we're doing developing math skills for Cambridge IGCSE Science, and my name is Mark. I'm Mark Winterbottom. I'm what they call an associate professor in science education at the Faculty of Education at the University of Cambridge. So really about 10 minutes walk from where Tamsin usually works in Cambridge. Lovely. So why on earth are we here actually doing this? Why do we care about maths and science? Why is maths so important? Well, it's kind of obvious, but scientists use data. And they use data in all of the subjects that we include in the science, chemistry, physics, biology, even going into engineering, etc. And we use data in all sorts of different ways, both descriptively to describe what's going on, and inferentially to try to make conclusions about what's going on. Also, perhaps more important and very fundamental for all of our audience today is that the syllabus says that we need to do maths and science. Now, I've copied, I think, just for biology maths criteria from the Cambridge syllabus, but bear in mind that what's required in the different science subjects will be different between each of those subjects. In this country, our government thinks maths and science is so important, it prescribes how much maths in terms of assessment weighting has to be in our domestic GCSE qualifications. So it's clearly something that people think is important, and they think is strategically important at a governmental level here and in some other countries around the world. So before we start to think about doing maths and science, I think we have to really try to get in the heads or move our heads into those of a mathematics teacher, because if we don't realise what the challenges are for students doing maths in our science lessons, then they're not going to do well in that maths. And therefore, they're going to lose a lot of assessment points when it comes to taking their examinations. So our first challenge is that students may lack mathematical knowledge and understanding themselves, which we really don't know about because we're not their maths teacher. So in many classrooms, maths is taught really as a series of techniques to be learned rather than as a set of understanding. So if a child's got an understanding of maths, they're more likely to see how maths applies when they're learning science. However, if they've just got learnt techniques, it's much harder them to see how to use those techniques in science. So we must realise that our children do arrive in our classrooms with gaps in their mathematical knowledge, which will stop them or may stop them engaging in maths for science, even if they tell you that they've done something in maths already. The second is that transfer. So the maths problems that people or that students usually face in science don't tell you what maths to use. It really isn't obvious to them. So if you're studying, let's say, graphs in maths, then the topic is called graphs. So you know it's about graphs, and therefore you're using graphing skills. If on the other hand, you've collected some data in a science investigation, no one tells you to draw a graph, and no one reminds you how to do it. So transferring that understanding and that knowledge from those techniques from maths to science is one of the real challenges. It's not just at school level, it's at university level too. And we know that from quite a lot of research, which has gone on already. Kind of obviously, not everyone likes maths, and I don't doubt people on this call don't like maths. Some of you will be excellent mathematicians, some of you will wish that maths never appeared in science syllabuses, I'm absolutely certain. For some people, that actually takes the form of a clinically recognised condition or a psychologically recognised condition called maths anxiety. Now, if you have a look at the screen, then you'll see a number of words which tend to be associated with that kind of anxiety. So embarrassment of getting it wrong, for example, maths being scary, being laden with concepts, people feeling inadequate or a sense of panic or fear. And in order, therefore, for us to think about that maths anxiety and to try to temper it and to counter it, we really need to think about what that means about a child sitting in our classrooms suddenly being faced with a mathematics task. So in the University of Derby, they define maths anxiety as unpleasant emotions and thoughts such as fear, dread and worry that appear in academic and life situations involving mathematical tasks. And they say it's got two dimensions. So one is cognitive, i.e. about what goes on up here in terms of thinking. It's related to concerns and worries about one's performance and potential failure. So many of you will be familiar with concepts of failure avoidance and not even trying to do the maths in case you can't do it. And then the other is about that more biological reaction. So the kind of reaction that you get when you're faced with a scary situation, it's very similar feelings to that. So the generation of feelings such as nervousness or tenseness. And because of that, it tends to be associated with a range of behaviours which include poor performance and general avoidance of maths. So you might find that some students who usually attain very highly in science suddenly do much worse in lessons which involve maths. And if they don't realise that that's the cause, then that could actually, destroy their self-efficacy in science itself. We don't want that. And then back to a different challenge, not anxiety, differences in the use of language. So, for example, in maths, the exponent is to the power, so 2 to the power of 10, for example. But in science, of course, power is energy per unit time. In maths, a line tends to be straight, but in science, we tend to talk about straight or curved lines. In maths, a histogram is a frequency density plot, but in science, it's a frequency plot. In maths, a range could be the range of a measuring instrument, but we tend to think of it as a range, top bottom of a set of data, and so on. So we've got to be aware that the way in which we use language in science, particularly in inquiry and investigative science, may well be different to how it's used in maths. Great. So how do we overcome those challenges? Well, number one, rather than focus on the maths, it tends to be better to focus on its purpose in relation to the science. So I would strongly suggest not to reteach maths in the abstract, but support your students in applying and building their maths skills in context. So let's just take a little example of that. And I'm going to call on Tamsin in a moment because I don't have interactivity with you, but I definitely do with Tamsin. So we're going to see if we can play with some graphs in the context of the Olympic Games. Now, why have I chosen graphs? Well, partly because in terms of motion graphs, students often struggle to connect the image of the graph to the dynamic situation it represents. They can see a graph, but they don't really see what that means, if you like, on the track in this case. So, for example, a horizontal line or a distance time graph means something standing still, but on a velocity time graph, it means a constant velocity, so something's moving. And practicing that kind of interpretation of graphs in realistic concepts that they can visualize in problem-solving situations then helps students to think about and understand the graphs. So, Tamsin, are you ready?
Yes, I am.
You reappeared. I can see you on my screen. Fantastic. So I'm going to put the first graph up, and then you're going to try to tell me which Olympic Games event the graph represents. So here we go. I will quickly tell you what the axes represent when I flick it up. Here it comes. So bottom axis is time, and the upright axis is velocity, which if you're not a physicist, Tamsin, we can just pretend that's speed.
Okay, so to me, so we've got some sharp banking velocity there over a short period of time. So I was thinking something like a high jump or something like that.
Oh, that's interesting. That's very interesting. So let's see what the right answer is. Drum roll, please. Here we go. Oh, no, it's 200-meter sprint. So let's go back and have a look at that. So, so here we are, time 0, velocity 0. So we've got people still, brilliant. So that's consistent with high jump. We've then got running faster and faster and faster. Okay, that's consistent with high jump and 200-meter sprint. Could it be? But it could be a graph describing both. And then the velocity stays constant. So I think this is where we've got a problem with the high jump. Because if you think about somebody running, getting faster and faster and faster, and then they jump, and they start to slow down, and then they stop. So in a high jump, we'd expect that graph to come right way down. But in a sprint, we're really expecting very quick acceleration, and then you can't go any faster, so you're running at a constant speed, and then the race is over. And so we haven't accommodated that bit where they slow down very suddenly, because that's where the race stops. Let's try another. Here we go. So that looks terrible, doesn't it? So distance on the upright, time on the bottom. See what you think.
Very intriguing. Okay, distance and time. Something like hurdling. So you're going, it's like a high jump again, but repeated, repeated, repeated.
Now, you have been more brilliant than you think, because you've got that sense of a period of motion with a break, and a period of motion with a break, and a period of motion with a break, which is fantastic. And if you've got your graph just coming down and then going back up, then you would be right. But look, there's a gap here, which is really weird. So how on earth do you go from really fast to 0 in a quick stage? And actually, ready for it? It's a 4x100 meters relay. So it makes sense now, doesn't it? Because you've got somebody starting at no velocity or no distance. They run, and then they get to there, and somebody else starts and they stop. So their distance stops, and the next person's distance starts. Look at that. One more. Okay, you ready? Here we go.
Oh gosh, right.
Vertical displacement. So in other words, how high you are is the one on the left.
How high you are. So again, this could be more like the high jump potentially.
It could be, you're right. So it could be more like a high jump. The only thing that dissuades me from high jump, because I secretly know what it is that we've got these little flat bits here. So that would involve running faster and then running at a constant speed, running faster or stopping, actually, vertical displacement, and then running and then stopping and then running and then stopping. And actually, you ready for it? 5, 4, 3, 2, 1. It's diving. And that kind of makes sense. Like you're walking up the steps, you walk along the flat bit, you walk up the steps, you walk along the flat bit, you walk up the steps, you walk along the flat bit, you leap into the air, you go boosh, splash, and then you come back up to the surface. So really thinking through these graphs in a realistic context really helps. So let's go back to where we started. Excellent. So what we've done is we've talked about focusing on the purpose in relation to science and putting it in that context. So how else can we overcome those challenges? So breaking that mathematical process down into really simple steps, which don't depend on, notice my italicization, but can help students to transfer their maths understanding from maths to science. So if we are trying to reteach maths and trying to build an understanding of the maths, we will take a long time and you will find it really frustrating. So what you've got to do is think, how do I scaffold them through the mathematical process? In the process, hopefully helping them to understand the maths, but definitely being able to understand how the maths services their needs in science. So it's a slightly different emphasis. And then number 3, support mathematical knowledge gaps, common challenges and differences in language. So for you to do that successfully, of course, you've got to essentially you've got to have the understanding of the maths yourself. Otherwise, it's just not going to work. Lovely. So together, all of these approaches combined should help us to build that self-efficacy back for those maths anxiety students, making each step achievable, dispelling myths such as only certain people can do maths, and reduce student anxiety about performing in front of you and their peers, and essentially getting them simply to put into practice a series of steps and being encouraged to think about those steps in the process. And that's what these books help you with. So we've got a math skills workbook for biology, for physics, and for chemistry. The way in which they help you is that they, for each of the areas of maths, they have absolutely the things that we just recommended. So they have a purpose within which the maths is set. So why is this maths important to science? We have a context and we have it step by step. So we've got it in action, as they call it here. And we've also got those step-by-step instructions. And we've got alerts for you and your students to alert you to what could be the knowledge gaps or the challenges in that particular area of maths, a little bit like we did in the graphs a few moments ago. In terms of the maths itself and how it's been represented in these books, the authors have split that into 5 areas, which I think are pretty good, actually. So representing values, working with data, drawing charts and graphs, interpreting data, and working with shape. I think we should say that these are represented perhaps to slightly different extents in each of the books because of the nature of the subject. So if we have a quick look at chemistry, you'll see a fairly even Steven split between the first 3 of those categories, and you can see the kind of structure to the book there. So you've got maths focus of using units, and then maths skills of choosing the correct unit, writing the unit symbol, writing symbols for derived units. And that's actually really nice because it shows you just how broken down the maths skills are here. So there's very little assumed about children's understanding in maths, but it's really broken down step by step. Then we've got quite a lot in doing calculations within chemistry, but not very much at all in terms of working with shape. Then if we go to biology, it's perhaps a little bit more of an even spread. We've got almost exactly the same amount, I think, although it looks like a different slide as for chemistry. And then we've got a real similar balance across all of those areas. So biology, if you're a biologist, you seem to be the most well balanced in terms of maths. Physics, physicists, no surprise. Yours suddenly looks very dense on the slide because there really is a decent amount of maths in physics, and wait for it. And this one looks even worse. Notice the font size has just shrunk so that I can fit everything into the slide. So there's a fair bit of maths and physics, as you know, and we kind of have to deal with that and go from there. So let's talk about then how we try to use the kinds of structures which are in this book in order to facilitate your lesson planning in maths. So we know the challenges, we know the maths that's included in the syllabus, and so we just need to think about how to plan effectively to deal with those challenges and to take it step by step for us. So we'll talk for at least one of the areas. We might do 2 or 3 depending on how we go, and then I've got a little fun for you at the end. So let's start with representing values. So representing values, you can see what it means on the screen. Students should be able to collect data and communicate the measurements they make. They should make sure that another person is able to understand their measurements. So how they write down those measurements is important. They must include the correct unit because it gives a number of value which helps other people to understand it. The students must be able to understand numbers much larger or much smaller than numbers they usually work with. Writing them in different ways, e.g. by using standard form, will make things easier to communicate. That's where representing values is represented in each of the sciences: biology, chemistry, math, and physics. And so let's have a little think through. So we're going to go for the particular area of using very large and very small numbers. And so our first step in any planning of maths is to identify the context, the purpose, and all the relevance. Now, it will be slightly different depending on what math skill you're using, but really we're putting that math skill into a real live context which shows them why it's important. So for example, in science, you've got to use very large and small numbers. The diameter of a strand of DNA is that. I'm not even going to try to pretend to read that number out. And there are around that many cells in a human body. Now, values written like this are hard to understand and say. I'm still almost tempted to try to read out a big number. I'm not going to in case I make a mistake. So it's easy to make a mistake and including fake numbers or miss some numbers out. And it takes a long time to write them. We use up a lot of space. And so for that reason, scientists often use standard form. So look what we've done. We've taken us from the problem or the contextual problem, and we've built towards telling our students about what the solution is in terms of maths. Then in terms of your own planning, you've got to recognize what the skill is, and you've got to clarify the language, and you've got to clarify that for yourself, and you've got to realize you're going to have to clarify that for your students. So look at the words here, and I've taken these straight from one of the books. We've got index, which of course has at least 2 meanings in English. So one is the thing at the back of the book where you look up page numbers, and the other is the small number that indicates the power. For example, the index 4 shows that the 2 is raised to the power of 4, which means 4 2s multiplied together. Power, of course, in physics, again, is energy per unit time. But here it's the number raised to the power, so or the exponent. So in a squared number, it's a 2, for example. Standard form, which if you were reading that just as an English language student, it wouldn't make any sense as mathematical notation. So you have to again introduce that terminology. It's notation, which a number is written as a number between 1 and 10 multiplied by a power of 10. For example, 4.78 times 10 to the 9. And scientific notation, another term, standard form. Then think about what those common problems are. Remember, we dealt with those 5 challenges earlier. So look more specifically now at what the problems are with this particular area of maths. Again, the book does it for you. So in standard form, the decimal place is always placed after the first non-zero figure. You can often get students writing 10 times 10 to the power of 10. That should obviously be 1 times 10 to the power of 11. So the conventions in terms of writing standard form are important to communicate. If you've got a lot of zeros hanging out, like that number down at the bottom there in the middle box, then students can be tempted to forget those zeros or not realize that they're significant, i.e. that they matter. And so you've really got to focus and watch out for students doing that, pre-warn them about doing that. And then again, not to forget the units in their final answer, because they're probably going to be different units from the number that they started with. So that proactively here is important. So think ahead, think through, what will this actually mean when I'm in the classroom, and how do I deal with some of these problems more proactively rather than just reactively? Then think about how to break the skill down. Now, I put in brackets here how you would teach it. So if you were describing standard form in a webinar like this and just reading it out, what would you say is the best thing for you to think here? What I'm strongly arguing, though, is that you don't say this. This is for you to get your understanding clarified. What you will do with students is in the next step, but it's important that you know what this maths is, that you have almost like a script for the maths. So when you get a question or when you see a problem, you've got that script to come to if you need to teach little components of maths. And you can see how that builds here. So with saying what standard form is and what its purpose is, we're then giving really broken down instructions as to how to do it. So let's do this one. Yeah, let's do this one. So large numbers in standard form. A number larger than 10 is written with a positive power of 10 in standard form. Really simple. How does 500 become 5 times 10 to the 2 in standard form? And look at the way in which the author of the book has broken it down for themselves. So 500 equals 5 times 100. 100 equals 10 times 10. Therefore, 100 equals 10 squared. Therefore, 500 equals 5 times 10 squared. So therefore, 500 and 5 times 10 squared are the same value. Now, if you haven't thought this logic through, then when you're circulating around your class and a child's got a problem and you diagnose that problem, then you won't have the script to be able to deal with that child individually and in a step-by-step way. So it's really important, this step, for you to think about how to break the skill down and how you would explain it to somebody. I don't suggest that you explain it to everybody, though. What I actually suggest is that you allow them to work through step-by-step instructions, which will help them to explain it to themselves, will allow the ones who are good at maths to get on, and also allow you to intervene where you need to. And this is even more broken down. So let's have a look. Convert the number 30,000 to standard form. Write the number as a number between 1 and 10. Okay, so it's 3. Count how many times the number has to be multiplied by 10 to get to the original number. 1, 2, 3, 4 times. Lovely. Convert the multiple of 10 into a power of 10. There it is, 10 to the 4. So it's 3 multiplied by 10 to the 4. Now look at that. It's simple. It's a skill that's been scaffolded by you by giving those step-by-step instructions. It allows them to see what these numbers mean, but it doesn't do a huge amount of abstract detail associated with it. Lovely. Now, in terms of the other areas, let me check my timing, see how I'm getting on. We've got working with data. We've also got drawing charts and graphs, and I think we will just have a quick chat through this one. And so here we are again. So identify the context, purpose, and/or relevance. So here I'm talking about why we want to draw lines, what's important about them, what a straight line shows, what a curved line might show, and giving that context. In chemistry, this may be the time at which a reaction stops and no more product is made. So first step. Second step, recognize the mathematical skills involved and clarify language. Now in graph drawing, there's a huge number of skills. Choosing axes, choosing the best axis scales, plotting the data points, using a ruler to draw a line of best fit, drawing a line of best fit freehand, and look at all the language that's associated with it as well. Now, any of these things can knock your students off balance. So really, you've got to take this step by step by step by step. And I'm not even going to think about skills 1 to 3 here. I'm just going to think about skills 4 to 5 for a moment. Then proactively consider how to approach common problems. Again, same thing. So students can find it hard to know whether to draw a straight line or a curved line. And in there, you're getting them to think about the science. Remember, if we've got a graph like C below, then we really can't say much about what's going on in between the data points because it doesn't seem to be a consistent relationship. If we've got a graph like A, then we probably can say something about what's going on between the data points because it looks like a consistent relationship. We may need to talk about anomalous points as well. And we also need to really focus on that 0, 0, because students will often force a graph through 0, 0, even if it doesn't make any scientific sense at all. Make sure when you're drawing that line, there's an even number of points above or below. Now, have a look at what's happened here. It's got to be right along the line. So here we've got points below down here and above down here. So that line's been skewed, even though it seems to fit the above below rule. So you've got to really emphasize the above below along the line. So we've got above there and we've got below here, but we're looking for that even spacing across the piece. Likewise, really simple things that the book points out really well. Useful to use the transparent ruler when drawing a best fit line. Avoid scales that make the values difficult to plot. It's not rocket science, but the students often will do it. To plot the points on the graph in the correct place, you need to work out the value of a small square. Now, that seems so simple, but it's one of the things that really throws students when using graphs and trying to plot their points. And then think about how to break that skill down. Again, this is for you, remember. Think what are the steps to drawing a graph. So you've got 2 axes, they've got different names. You then need to put your tick labels on to indicate the scales. Then you need to give the axes actual names with units, so you know what units you're working in. Then you plot your points. And you do it either as little crosses or little dots with circles around, they recommend in this book. And then if they show a continuous trend, i.e. there seems to be some relationship there, then you can draw a smooth best fit line. This clearly looks like a curve, and therefore we're drawing it as a curve and probably fits the scientific context too. And then do those step-by-steps. Now, I'm not going to go through all of these, but I'm just going to show you just how step-by-step the point plotting is being done here. So find the values of a pair of measurements, coordinates on the axis. That's our job. So first, we find the value of each independent variable on the x-axis. So let's say we've found 1. And then the corresponding value of the dependent variable on the y-axis. So let's say we've found the 9 here. Then step 2, find the point where they intersect. Now, look how step-by-step this is. Track vertically upwards from the value on the x-axis and track horizontally sideways from the value on the y-axis until those 2 lines intersect. They intersect there. That's where you put the point. Now, that sounds like your students won't need that much step-by-step, but you may well be surprised. And for those of you who haven't ended up with a graph taking all lesson, then you must be geniuses, because graph drawing can throw students so completely. So I'm not going to talk about the rest of the step-by-step of the line of best fit, but I just really wanted to use that to show you the need to do it as simple and as in small increments as you can. Lovely. So I'm going to whisk through and just come to the final part. And for those of you who are biologists, I've popped this in. I'll let you look at it later when you get the slides. But the surface area component of thinking about biology is often one which causes the most challenge. And I think particularly the biology book here really does help you with that, particularly in terms of calculating surface area and surface area to volume ratio. Lovely. So what have we talked about? We've talked about that building understanding in context as being really key. And what I've done here is given you a site which links to an initiative at the University of Cambridge, which is called Enrich. And it gives you a number of different mathematical problems which take you from context to understanding. So if you think that your students really, you can make a difference to their mathematical understanding in your lessons, and have a look at biology, chemistry, or physics Enrich. And you can just Google Enrich or Bio Enrich or Chem Enrich, and you'll find it. Otherwise, the links are all on the slide here. And then finally, a really nice thing, which one of my colleagues has done, particularly in relation to graph drawing, is the physics of birdsong. And I thought we'd just finish with this because it's quite nice. Tamsin, have I got time? I'm sure I have. Let me have a little look.
We can do a very brief one.
Brilliant, excellent. So let's whisk through. So let's think about birds. Birds sing, la, like that. And oh, actually, I'm wondering if you might or might not get the sound here. We'll just test out. Can you hear that? No, Tamsin can't hear it. I can see she can't hear it.
No.
In that case, what we'll just do is quickly move through. So think about the way in which graphs draw, and think about the way in which students may hear it. So, for example, if I make it sound like this, la, then I'm going really in a straight line, time versus frequency. So I draw the graph like that. If, on the other hand, I'm going like this, la, 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 then I would have a line, a gap for the quiet bit, a line, a gap for the quiet bit. And if you take this forward, then really build your drawings, they're making graphs of them. And then as we go forward, and when you get the PowerPoint, you can play with it, then we can listen to the chip chat and we'll draw a graph of it. So the chip chat goes, and so our graph will go rup, 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 like that, which will be really rather nice. So lots of birds for you to play with going forward. And I'm going to snip through just to reiterate about the resources we use today. You may like to look at a free product from the Association for Science Education about language of maths and science. We have got stem.org.uk, which has some nice resources on mathematical skills and triple science. We've got STEM Enrich, which we talked about before. We've got the Physics of Birdsong games. And of course, we've got the books, which quite frankly are, well, they're on my shelf already, let's put it that way. So, so they're good things. And I think that's me done, Tamsin. So I am going to wave goodbye from a lovely King's College in Cambridge, which was rather serene and wintry, I think, with no leaves on the trees. And I'm going to hand over to Sally. So Sally, it's all yours. I need to work out how to stop sharing my screen now, which is rather scary. And mainly because you've all jumped to a different part of my screen during the presentation. Hang on. Oh, this might be where it all falls down, Tamsin. A seamless unshare. It's going to go wrong. There we are.
Brilliant. It's working.
Lovely.
Now Sally can take over.
Thank you, everybody. Thank you, Tamsin. Over to you, Sally.
Thank you so much, Mark. Some excellent ideas there. So my name is Sally, and we're going to concentrate on the English now, and how you know, the fact that our students are learning science through the language of English, and we're going to have a look at some of the challenges that our students face, and actually that we face as well as teachers. So think about some of those excellent concepts and strategies that Mark introduced, and you might see some connection with the English skills going forward. So to start with, really it's about thinking, how can we support our students when they're learning and they're studying IGCSE science, but through the language of English, which is not their first language? So here are some of the broad areas that we need to just think about to start with. So students may be studying science and think, okay, I know what this word is in my language, but actually, how do I say this in English? It could be a vocabulary issue. Also, thinking about vocabulary, sometimes students know what these words mean in everyday language when we're generally communicating, but potentially they've got a very different meaning actually in the area of science. So what does it actually mean in the context of science? And also, it might be about thinking more along structures now. So how do I actually explain this scientific process within the language of English? I know how to do that in my language, but how do I explain this in English? And very often, one of the many functions that students are required to use is about predicting. So how do I actually predict what's going to happen in my scientific experiment? How do I do that in English? So these are just some of the broad areas that we need to think about. To start with, we're going to focus purely on vocabulary, and you will notice that there are lots of crossovers as we go along. So what are the main challenges in terms of vocabulary when we study science? So, as I've suggested, words have very different meanings in everyday language compared to their application in the science classroom. So culture is a really good example here. So in everyday English, we can think about culture in terms of, the ideas and the customs that we live by. But of course, in science, this could be bacteria culture or cell culture, and it has a wildly different meaning. So it's being aware of some of those differences, and you might just catch, when you're working with your students, that you might just identify sometimes that they may know the general term, but they haven't really understood the difference in the meaning within the science classroom. And also, from our point of view as teachers, how do we know what vocabulary learners will need in that lesson to support with the area of learning that we're focusing on today? And also, how can we help our learners to boost their scientific vocabulary? Like with all subjects, it has a particular set of words, vocabulary, and phrases that students need to understand and also be able to use to explain their ideas. What do learners do when they read a word that they don't know in science? So it could be reading part of a textbook, for example, and they come across a word which they just haven't seen before and don't know the use in science. So how can we help learners to decode some of these words? Okay, so those are some of the issues or maybe challenges that our students may face. So what are the strategies? What can we do to help our learners? Well, as teachers, when we are in the planning stage, this is when we can really think about extra support that we can provide our students to help them through some of these issues. So for us as teachers, it's to think about, well, what key vocabulary do my learners need for this lesson? And as Mark suggested earlier, we might not be fully aware of exactly what their needs are at the start. But if we just think about, okay, so the topic today is this, what are some of the key words that they are going to need? And have that support ready so that some students may not need any support, but I'm sure most will. So if you've got that strategy, then you can use that to help the learners, or the learners can use that support to help themselves even better. And also to check the specific meanings of words in the context of science. And coming up, I'm going to show you some great examples of resources that you can use in order to do exactly these types of points, or to support these areas. I think a really good way, I'm a visual learner, so this definitely works for me, but to use real, which means real objects. So in our science classrooms, science labs, it's full of equipment. So actually using real objects to help learners to understand vocabulary is a very powerful thing. If you haven't got access to maybe something you need, then of course we can use pictures. And also a really good technique is to use questioning, really just to check what vocabulary learners have already, and maybe some gaps in their vocabulary that we might need to support students with. Using prefixes and suffixes, so the bits that we add at the beginning and the end to English words, can really help our learners to expand their vocabulary and have a better understanding of what they're reading, and maybe guess, but guess in an accurate way, if that makes sense, so some of the new vocabulary that they come across. So some examples of prefixes could be photo. So if our learners understand that photo is connected with light, then it almost decodes maybe some other words that they've not come across. So, you know, photosynthesis is one example. Another example is tele, meaning far. So, for example, telescope. By is a great example of a prefix as well. And actually it can mean life or it can mean two. So in terms of life, we can think biology, for example, that's a nice example. Or thinking about the idea of two, it could be binoculars, for example. So just having an awareness of some of these prefixes and sometimes suffixes as well, it can just help learners to think, that must have a connection to light, for example. And it just helps students to decode themselves. Also, to think about the context in which these words appear, so that again, the students can have a good educated guess. That's the phrase I'm looking for, to think about what their meaning is within that context. Always really helpful. For me, this is a huge takeaway, is to encourage our learners to create personal scientific dictionaries. So, you know, students very often use possibly paper-based or online dictionaries to discover the meanings of some new words within science. However, that's pretty passive, you know, just to look something up, it's this. And if we don't engage with that vocabulary, well, certainly for me, in my experience, I will just forget. So if we can encourage learners to keep a personal scientific dictionary, so it could be just a notebook, page 1 is A, page 2 is B, etc. And the students write down any new vocabulary that they come across, but then look up the definition, but to write it then in their own words. And by doing that, they become more active in the process and much more likely to make a stronger connection with that new word, and more importantly, to remember for future usage. Also, what I'd encourage is for students to use that word. So write a sentence using that word, but again, in their own words, their own idea. And again, it's activating the language. So definitely, if you've never thought about encouraging learners to do this, give it a try. It is really, really powerful, I would say. So moving on from vocabulary now to structure. So let's take a look at some of the challenges first of all. So of course, learners will need a range of different English language structures in order to communicate their ideas. And this is something, again, that has a connection with what Mark was talking about. So it's not about teaching maths or English in the science classroom, but it's making those connections. So, you know, it's all about cross-curricular work, isn't it? So, you know, what the students have gained from their English classes, can they then transfer those skills and apply them to the topic of science or the subject of science? Command words are huge in science. So, you know, can our students actually explain, describe, predict things within science? So these are some very key areas that I would probably say happen every lesson. It's needed every lesson. So those are some of the challenges. So what strategies can we use to help our learners? So again, from our point of view as teachers, we need to think about the planning stage. And just like we said for vocabulary, it's to think about, well, actually, what structures do my students need in order to communicate their science ideas and knowledge in today's session? So if we can have a think about that to start with, then we've got a good chance of helping our learners to accurately and effectively communicate their ideas. And these are just some ideas, some examples of what they may need. So they may need adjectives to describe things. So it could be physical objects, it could be processes even. Very often we're asking learners to compare. So, you know, which is, I don't know, which is hotter, or, you know, which is the biggest, we could say. So always we're asking students to compare and to talk about the top of the range or possibly the bottom of a range of data, for example. So how can students compare materials, properties, etc.? I've used this word predict quite a lot, and I think we do a lot of this in science. So do students have the structure in order to predict what they think may happen in an experiment? This is a really common situation, isn't it? So like my personal science dictionary idea, that's one of my key takeaways, this is the second one. And I don't know if you've come across this idea before, but CLIL, and it means content and language integrated learning. So CLIL lessons have two focuses. Of course, the key focus is the scientific content, but running alongside that is an awareness of, or a consideration of, the language content that the students will need to access or use in order to be effective in their science. So content is the science, but the language learning could be thinking about the vocabulary. It could be thinking about the structures, actually, that the students will need. The good news is that the resources that we're going to have a look at in a moment support you in this area. I think it would be a bit mean, wouldn't it, to ask you as the science experts to be suddenly English experts as well. So the resources are there to give you that extra support as well. So as well as vocabulary and structure, I also wanted to sort of expand this out to think about the 4 skills. So the reading, writing, and speaking and listening, which is involved in science. So let's think about some of the areas in terms of these skills. So reading, well, unfortunately, English is not a phonetic language. So how the words look on the page is really different to how they're pronounced, which is quite typical of English, isn't it? So it might be that recognition of words is a challenge for learners. If we just look at these 3 examples here, larvae, gauge, and debris, you know, they don't sound like they're written. So this is a challenge for reading. And also you might think about what we call first language interference as well. So it's human nature to apply our first language structure onto other languages that we use. So for example, Ken, welcome from Indonesia, and all of our other teachers joining us today from Indonesia. So just one example, Bahasa doesn't really have tenses, and I'm quite jealous of that. But instead, rather than adding like we would in English, ed to make it the past, there would be specific words to say, you know, maybe, you know, yesterday, tomorrow, today. And that's how the time frames are communicated. So, you know, it's worth thinking about, you know, first language and how that's applied to the use of English, and see if you can spot any key areas that you can help your learners with. Writing. So I suppose this has got a connection with the idea of English not being phonetic. So can students spell effectively? Of course, you know, if they're doing a science task, you know, we're not really looking for 100% spelling accuracy, but it needs to be accurate enough in order for the reader to understand the ideas that are being communicated again. So sufficient spelling is necessary. Structure, we've talked about quite a lot already. So, do they have the structure to be able to write their ideas? And it could be the format as well. So, do they have to write notes? Are they expected to write maybe a deeper, essay type explanation? And then finally, speaking and listening. So very often students read information and they have to write their answer. But also speaking and listening in terms of studying science is so important as well. Again, it's got a connection with English not being phonetic. So pronunciation, do students know how to pronounce words, again, accurately enough to be understood? And also, I think it's definitely speaking and listening. Speaking in particular is very much connected with confidence. So Mark talked about maths anxiety. I can identify with that, but it's the same with language learning, isn't it? That we want to build, a safe learning environment so that students feel confident really to ask questions. If they're not really sure, to have that confidence to ask. And paraphrasing as well. So something might be presented, I don't know, on a video or in a textbook, and it might not be 100% clear. So being able to paraphrase in order to explain things more clearly is very useful as well. And I think actually students are really good at paraphrasing. Oh, it means this. I think that they are particularly strong with this. So strategies, of course, there are too many to cover in the time that we have together. But it might be just one idea is to think about the letters and the different sounds letters have in words. So for example, when students are reading, do they know that the C can sound like K, but it also can sound like S, especially when it's followed by I, E, or Y, for example. And this also has an impact on pronunciation. So not just reading, but pronunciation and also spelling. So it has an implication for all of the 4 skill areas. So I talked about, we really want to encourage a very open and sort of friendly environment so that students don't feel silly asking questions. I know this is a science lesson, but it's okay to ask language questions because it's very, very important. And then it's, how to rephrase explanations, ideas, so that the clarity is there. So moving on, I'm just checking time. My goodness, time goes so quickly. So now I just want to give some practical examples of resources that can support you as science teachers with English in your science lessons. So as Mark mentioned, we have these 3 skills books. So as well as maths, we have English language skills books too for IGCSE Biology, Chemistry, and Physics. Some of these things are familiar from Mark's session, so I've got the luxury that I can skip through a couple of things. So just as with the maths books, it's the same approach with the English books. So at the beginning, it's got a skills grid. So it goes through each chapter and it also presents what English language structures, vocabulary, functions are attached to that chapter. So you can really easily identify. So for example, if you're looking at classifying living organisms, you've got a clear indication there that the present simple tense is very likely to be used. So what can I do in terms of planning? Think about the CLIL idea with the content, but also the language. So are there any particular vocabulary items that I need to be prepared for in case my learners need support? And the same with the structure. So what structures do they need? And again, the resources just help you as science teachers. You know, you don't have to try and figure out what that is. It's actually presented here in the resources, which is really helpful. Also, a feature of the books, as well as the grids which really clearly point out the language which is needed or connected with, there's also a reference section. So it goes through lots of different structures and gives, you know, some examples within the context of science. Remember, it's broken down into, you know, biology, chemistry, and physics, of course. So, you know, they've got some nice examples here. So, for example, this quick reference guide here, a noun, what is a noun, and some examples of biologist, for example. And it goes, you know, a bit more deeply into modal verbs and various different tenses. So I won't have time to go through all of these, but you will get the slides so you can have a look at some of these examples in a bit more detail later when you receive them. However, the process is very similar for many of these activities. So you've got the quick reference guide, so you can take a look at the language and look at the explanations. And then there are lots of tasks and exercises for our learners to use and practice. So this example is very much about keywords. So again, it helps us as teachers. We don't have to figure out what the keywords are. It's actually presented for us. So it might be that you get your students to take a look at this key vocabulary, identify any which are new, and then maybe encourage learners to keep a personal science dictionary so they work out what these words mean in this context. And then they have an opportunity to try it out. So use those keywords within the task. Here, this one is very much about making the connection between everyday English and the words used in a scientific context. So we've got one example here at the top, factory, and it's give the general English meaning. It's talking about the application within science. So there's one really nice example there. And then there are others for the students to take a look at this word bank and try and make a connection. And it's, again, awareness raising of the difference between general English, everyday English, and those words used within the context of science. So really nice examples here to support that challenge. And then this is moving on. So using that previous slide, then it's just taking it a little bit more deeply. So here they're looking at the words and the meanings, and specifically the meanings in science. But then they've got this deeper opportunity to use these words. And a bit like I suggested for the personal dictionary, it's about encouraging learners to use these words, but in sentences of their own. And it activates the language much more effectively, I would say. We don't have to be, language learners and be very strict and, formal all the time. We can encourage our learners to have a bit of fun as well. So maybe word games within the books, there are opportunities for things like crosswords, word searches, and it's just a more fun way really to activate this language. So, don't be afraid to have a bit of fun with the language as well. Here we've got, again, keywords. And this is a connection to cross-curricular areas. So it might be that these words are important and used in many different subjects. So they might have had some exposure to these words previously. But then it's about, well, how can I expand that vocabulary? So at the bottom here, it's very much about the different types of words. So nouns, verbs, adjectives. And how can I use these words in slightly different ways? So singular, plural, are there any irregular ones that I need to know about? So all of these activities are very useful. And it's very much, a lot of the processes are very similar. So I suppose we can say it's like exposure to the language, and then to try using it out in various different tasks. And that's a really good way for us as teachers to check their understanding. So when they're applying it to these tasks, we can really see, it reveals how well they understand that piece of language. So moving on to structure, I know I'm sort of out of time, so I'm going to go fairly quickly through. But in terms of structure, here are just some more examples of the support that you can find. So it supports us as teachers, but also these are workbooks which are intended to be used by students as well. So it's support for all of us. So keywords, again, Mark showed some keywords within maths for science, and it's the same with English. So some nice, clear definitions. And then what I like about this one, even though I'm talking about structure, it makes a connection with the 4 skills as well. So we're asking learners to engage with a reading activity, and it's looking at some of these keywords in bold within the context. So remember earlier I talked about, thinking about words within context, and it helps us to understand how those words are used. And then again, there's an opportunity, so exposure, examples, and then an opportunity here at the bottom for students to apply those key words. And this time, because it's about structure, it's, what type of word is that? And, is it a verb, for example? Is it a noun to label something? And how do I use that in language of my own? We've also got things like the conditional tenses are very, very helpful in science. So to make predictions, students will need the first conditional. So you don't have to suddenly jump from being science experts to English experts. You've got a really nice example here of the structure. And again, it's examples within science. You've got some examples in sentences here, so the structure is then applied. And then once again, it's got an opportunity for the learners to try it out, to construct sentences of their own using this structure. And in the language focus box here to the right, it just gives extra support and more examples. Connectives is just one other example here. So very often we want to talk about cause and effect within science. And if we do this, this is what happens, and this is what happens because of this. So connectors are used and opportunities again to practice these is there. The resources are there to support us and our students. And also, so we looked at connectives there, and I guess this is a similar thing. Sequencing is vital in science. So it's giving students some ideas of how they can organize the process of what they're studying. So it might be explaining an experiment that they've done or a process that they've gone through. So using things like first, after that, next, and then for the final element, we can say finally to introduce the last step in the process. And again, there is an opportunity, so an explanation, and then there is a piece of reading in this box which has no sequencing at all. And then students can use this example then to write out and try out using these sequencing features in order to better explain the process. Thinking about the 4 skills, this is where we, potentially, we can use these resources and stretch them and use them for wider things. So here we've got an example of a text to read. It's pretty short, but really the reading skills is very much about looking out for keywords and selecting specific information in order to answer the question. So this is definitely reading skills. Moving on to writing, here we've got some keywords. So everything is very much connected, but keywords, and I suppose it's great support for things like spelling. Think about characteristics. So we know that CH is normally ch, but sometimes we have these irregular situations where the CH sounds like k. So it's a really good support for spelling, but also because of the gap fill, it just helps learners to connect with, well, what type of word is that? What in that gap, what sort of word do I need? Do I need a verb? Do I need a noun? So it's, again, reinforcing the structure of the language. And once again, there's a really beautiful step and process. So exposure, supported application, and then a freer application where learners can use this vocabulary, but use it in structures of their own within writing. And speaking and listening, I suppose this is where, we can get a bit creative with using these resources. So because it's a workbook, a lot of the activities are really to read and to write, but why not use them in the classroom and use them as opportunities for discussion? So here we've got language for giving advice, things like you should, you shouldn't. So that's really a perfect opportunity to use it and extend it to speaking and listening skills. Even though it's presented as a writing task, why not expand it to speaking and listening? So I think, went over a little bit there, but I think I've managed to get all of those things in there. So it's over to you. Any questions?
That's brilliant. Thank you so much, Sally and Mark, for a fascinating presentation there. Just before we start the Q&A, I'm going to launch a poll. We'd be really interested to hear about your main teaching challenges at the moment. So you should see that appearing on your screen just now. And in fact, as we've run over a little bit, why don't we start the Q&A whilst that's running in the background? So we'll let that keep going there. So if there are any questions for Sally and Mark, could you please put those in the Q&A box? Okay, let's start with one for Sally here. Which dictionary could we have to recommend to students? So Sally, are there any particularly useful dictionaries for working with science?
I can't think of a title off the top of my head right now. There are various versions, but I would just recommend, a student's version. So don't go for, the full, dictionary, which is for first language speakers. Definitely choose a learner dictionary. So maybe I can have a look for some particular titles and pop that forward later, but definitely go for the learner versions, not the regular ones.
Fantastic, thank you, Sally. And also to note that at the back of our workbooks, we do have a glossary function as well, which would be really useful for students, wouldn't it, Sally?
Definitely, yes.
Fantastic. Okay, so another question for Sally. Is there a trick to make our English pronunciation fluent for beginners?
Okay, so for me, I think it's very much about studying the letter combinations. So, you know, as I suggested in the session today, you know, just things like, you know, how the letter C and the letter G behaves when it has certain letters following it. So how sometimes it's the G sound, sometimes the J. So if we can connect with those, you know, with those common patterns, I think this is particularly helpful. And it's also, you know, to be aware that we have so many irregular quirks as well. So maybe to study some of those common exceptions to the rule as well, it is really helpful. I think, sorry, just to add to that, you know, it might be about listening. So using videos within the classroom as well, so that the students can listen to models of the language could also assist.
Brilliant. Thank you so much, Sally. I think for the moment, those are our only questions. If we do get any more that appear in afterwards, we will obviously get some answers to everybody. So it only leaves for me to end the poll right now, and it'd be interesting to share the results with everyone. So interestingly, coming out on top for major teaching challenges to everyone attending today, we've got English as a second language learners, followed up at 37% with preparing my students for assessment. So it's interesting to see those are the biggest challenges. And we were also interested in your current teaching situation. So we're seeing 49% edging above we've got in the classroom, but we still have a mixture of blended learning going on there. Fantastic. Right, let me just remind you of a few things before we end the webinar today. So thank you so much everyone for participating, and thank you so much for attending. Remember that 7 days after the webinar, we'll send you an email thanking you for your attendance with a link to the recording of the webinar and the webinar slides. You can use this email as proof of your attendance. To find out more about the resources discussed today, please speak to your sales representative or visit cambridge.org/education/science. So, but thank you so much, Mark and Sally, for that fantastic presentation. It's been absolutely brilliant today. And thank you everyone for interacting so much. When the webinar ends, a short survey to complete will open on your screens. Thank you for any answers you provide. Good luck with your teaching. And goodbye.